Right, check it out, everybody. So in chemical kinetics, mainly it is to do with the rate of the reaction. So we will learn point by point. First, you learn the basic definition of what is rate. So rate of chemical reaction is how much is the magnitude, what is the magnitude of change in concentration of reactant, reactant or product, reactant and product with respect to time required for that change to happen. Got it? And this is always positive term. It's always a positive term. Yeah. Generally, we can categorize chemical reactions into three kinds. One is very slow reactions, then fast reactions, and then moderate reactions. Yeah. Like rusting of iron, okay, or weathering of rocks. Yeah. So this is a very, very slow process. While if you notice instant or fast reactions here, that include anything, detonation of explosives, detonation of explosives, acid-base reaction, acid-base reactions, precipitation like AgCl precipitate, BaSO4 formation, like this. Any precipitate reactions. Okay. Then we have moderate type of reactions. All right. So moderate reactions are those which would have sufficient amount of time. So they are not too fast or not too slow. Okay. So H2 plus Cl2 combination in the presence of light, that's relatively moderate. Then decomposition of you know N2O5, decomposition of N2O4, yeah, ASH3, and ester hydrolysis, ester hydrolysis, and hydrolysis of sugar. Hydrolysis of sugar. These are few basic examples. I mean, I'm exclusively touching only those examples which have been generally asked in the PYQs. Okay, these are the ones which have been asked earlier in PYQs, so just be focusing on that. Okay, next, when we see the chemical reactions for any reactant, suppose if at all I take a reaction, let's say I say this is reactant going towards product, got it? Then the average rate will always be equal to total change in concentration with respect to time taken, and we typically write it this way: the change, a reasonable amount of change for reasonable amount of time. But if you write instantaneous rate, then that would be limit delta t tends to 0 mod of c by uh, delta t, or c by delta t, which we could write it as dc by dt, dc by dt. Okay. If you write in terms of reactants, then it will be minus dr by dt. In terms of products, then it has to be dp by dt. The negative charge implies that the reactant concentration is always decreasing. Positive sign implies that it is always increasing for product. Okay. Graphically, how it looks like, I'm pretty sure you have come across that before, so I'm not getting into the details of it. Okay. So if needed, I'll send you my class notes again, old class notes, so that you get an idea once again. Okay. Now, typically, what you need to be more observant is on the reaction rates, reaction rates, and their stoichiometry. Reaction rates and stoichiometry, how it varies. Correct. So if you have a general reaction, AA plus BB is giving CC plus DD, then rate of reaction, rate of reaction will be always equal to 1 by A dA by dt is equal to minus 1 by B dB by dt, and whatever I'm writing is all instantaneous rate now. dC by dt is equal to 1 by D dt by dt. Again, you don't have to get into the proof of it or waste time in that. Just remember it. That will be more easier. Correct. This will be the rate of reaction. Okay. Now, when you write the rate only in terms of the reactants or only in terms of the product, that is, if I write it this way, minus dA by dt, then I will read this as rate of disappearance of A. Rate of disappearance of A. Appearance of A. Similarly, if I write that in terms of C, I would write this as dC by dt as rate of appearance appearance of C. Correct? So remember the terminology used. When do we use rate of appearance and rate of disappearance as such? Okay. Clear. Now, what are the methods that we use? Methods that we use to to represent the rate as well as how to interrelate each other. Okay. Suppose let me take one example. 3A gas is present with 2B gas plus C gas. In that case, I can write rate of reaction is equal to rate of change of A by 3 and rate of change of B by 2, that is equal to rate of change of C by 1, which we can write it as minus dA by 3 times of dt plus dB by 2 times of dt, which is equal to dC by dt. Okay. This can also be represented in terms of change of number of moles of A, because concentration can be written as number of moles by volume. So the same thing I can write rate is equal to minus dNA by 3V dt is equal to minus dNB by 2V dt is equal to minus dNC by V dt. We could write the same thing in terms of weights also, or we could write in terms of partial pressures also. If these are gases, I can also write it as minus dPa by 3 RT into dt, which is equal to dPby, okay, 2 RT into dt is equal to dPc by RT dt. So depending upon whatever the parameter that is given, use that accordingly, find out this value. Okay. How questions are framed in this sense, check it out. If it is been given the rate of disappearance of you know MnO4 minus is given, and that is 4.56 into 10 raised to power of minus 3 molarity, second inverse. Find rate of appearance, rate of appearance of iodine. Okay, I2. Clear? Now, for that sense, you have to imagine, and this will be given in acidic medium. The medium will be given to you. So, in acidic medium, MnO4 minus will react with I minus in acidic medium to give Mn2 plus and I2 plus H2. Typically, you need to balance the reductant and oxidant. So you know that from here to here, 5 moles are transferred, 5 moles of electrons are transferred. From here to here, 2 moles of electrons are transferred. So if I counterbalance that, I will get it as 5, 2, 2, and sorry, this is 10. 5, 10, and here 5. Okay. So 2, 10, 2, 5. These are the balanced forms. So using that, now I can write rate of reaction. Rate of reaction is equal to, right? Rate of disappearance of MnO4 minus by 2. That is equal to rate of appearance of I2 by 5. And that's what you need to figure out here. So rate of I2 is equal to 5 by 2 times of rate of MnO4 minus, which is already given to us, 5 by 2 into 4.56 into 10 cross, into 10 raised to power of minus 3. So this kind of questions, you should be able to do it easily. Okay. So please make sure that you are aware of these terms. Okay. Next. Suppose if a question is given this way, N2O5 is decomposing to form 2 NO2 gas plus half O2 gas. Okay. So it is given first order reaction, and you need to find ratio of K N2O5 is to K NO2 is to K O2. Clear? And this K represent rate constant here. K represents rate constant. So again, rate of reaction will be equal to rate of N2O5. It is equal to rate of NO2 by 2 is equal to rate of O2 by half. Isn't it? So rate of reaction generally is always written as K of the reaction into N2O5 raised to power of 1, because I have given it as first order. Clear? Now if at all I have to write rate in terms of N2O5, then it will be rate constant of N2O5. There is always this confusion between these rate constant values. So be careful while writing the rate in which terms you are writing. Okay, this will be the one. Rate, if you are writing in terms of NO2, then it will be rate constant in terms of NO2 versus N2O5 power 1. And rate of O2 is equal to rate constant of O2 into N2O5 raised to power of 1. Now, if you take the ratio of the same, so I write K of the reaction will be equal to K of N2O5 by 1 is equal to rate constant of NO2 by 2 is equal to rate constant of O2 by half. Correct? So the ratio of KN2O5 is to NO2 is to O2 will be equal to 2 is to 4 is to 1. Correct? There is this, please be careful with the confusion between the rate constants. In which terms the rate constant is given? Is it given for the reaction, or is it given with respect to the reactant or product? Okay, next. You got to understand the term what is differential differential rate law equation. See, if you have A plus B is giving something like, 2C or something, these are all gases, imagine. Then rate of reaction will be equal to rate of the K of reaction into A raised to power of some X and B raised to power of some Y. Okay. Where X is called the reaction, order of reaction with respect to A. Y is called order of reaction with respect to B, while X plus Y is termed as overall order of reaction. Clear? X and Y are experimentally found, experimentally determined. Clear? So you could imagine what is the rate order definition. Order is the sum of the power of concentrations of the chemical species in the rate law equation. So what we have written here, this is called rate law equation. Rate law equation. Got it? Now, order could be of anything. It could be fractional, could be plus minus everything. Yeah. So we will come to that. We'll understand what are the differences there. Okay. Now, before going further into the idea of how to calculate the order of the reaction by various methods, first let us figure out what are the factors affecting rate of reactions. This is a direct question given as various options. Figure out factors which depends on them are concentration, then temperature, then nature of reactants and products, reactants and products, then catalyst. What is the catalyst we are using? That will also influence the rate. Next, pH of the solution. If you are talking about any solutions here, then dielectric constant, dielectric constant of medium. We have radiation or light, pressure. Pressure is an important component. Next, electrical and magnetic field. So these all options are correct, everybody. Okay. So please remember, rate can be influenced by all these factors. Okay. In our cases, generally this is all the dependency. But in all our cases, while solving the questions, we expect only the first four things are influencing the rate. Correct. The rest of them, we always try to keep it constant. We are not changing these kind of parameters.
Sir,
Yes, Vitu.
sir, how does electric constant affect the rate?
How does electric
Sir, dielectric constant of medium.
dielectric constant of medium? Okay. So basically, if you have uh, ionic reactions, imagine, okay, reactions are happening between the ions, then the polar medium will always delay the reactions. The non-polar medium will make a reaction faster. Correct? You would notice this when you have SN2 type of reactions in organic, isn't it? Polar protic solvents, right, would influence in certain reactions. In polar aprotic solvents will influence in some of the reactions. Let me give you an example. Suppose if you have RCl plus NH3, right, then you will get RNH3 plus Cl minus, correct? Now, if the reaction is present in a polar solvent, the reaction is more favorable, although it is SN2. It is more favorable in polar protic solvent. Okay. because polar protic can actually keep these ions far away from each other, enhancing the reaction to happen faster. But if you make some reactions like you have RCl plus OH minus, and then you are getting it as ROH plus Cl minus, right? This is also SN2, but this time polar aprotic solvent is more favorable. So its polarity is less, its dielectric constant is less. Here dielectric constant is more. So it is influencing the rate of reaction. Understood, beta?
Yes, sir.
Right. So these are the factors which will influence, but like I said, most of these factors we will ignore it except for the first four factors. Okay, right. Now let us see if you have to figure out what is the order of the reaction. We will first learn one more term, which is molecularity. Molecularity. Molecularity is about the number of molecules that are present in an elementary reactions. Correct? It shows that a reaction can be again classified into two kinds. One is elementary. Elementary is always about one-step reaction. One-step reaction. In one-step reaction, you will see no intermediates forming. While if a reaction is called complex reaction, then we say it is multi-step reaction. Multi-step reaction. Here, at least one intermediate is formed. At least one intermediate is formed. Okay. Now, if you compare molecularity is basically suggesting how many number of molecules are present. Molecules are present in an elementary reaction. In an elementary reaction. All right. See, in organic reactions, we also say take this as molecularity is number of molecules, present in rate determining step of the reaction. Okay. But molecularity of a complex reaction is not defined. Molecularity is only defined for elementary reactions. But within the complex reactions, if different steps are given, let's say, I'll take an example here, a complex reaction. Complex reaction, it is going from first A to B, then B is going from B is going towards C to D. Okay. Then C plus A is again going to some F, which is a product. Let's say this is what it is as the product. And this is a fast step. This is a slow step. Sorry, this is a fast step here. And this is a slow step. Okay. So, as a general statement, if you see as a general statement in NCRT also, it has been mentioned, the molecularity of complex reaction is not defined. But if a rate determining step is given, the slowest step of the reaction is the rate determining step. And if a rate determining step is given, within the rate determining step, you have to see how many molecules are involved. So two molecules are involved. Then I can say the molecularity of this reaction is 2. But the 2 is actually with respect to the RDS only. Okay. So if a general statement is given, you please take it as correct statement only that the molecularity of the complex reaction is not defined. But at the same time, if the same statement is given with respect to a rate determining step, then it is defined. Okay. So just be aware of these two terms, okay, everybody. Now you notice that since molecularity is just the number of molecules on the reactant side which are taking place, while order of the reaction is the experimental value. So that's the main difference between these two. Okay. Now, basic pointers we need to know about molecularity, molecularity and order. If you compare, right? So molecularity is always a whole number, while order could be any rational number. Here, any fraction or integer. Here, next, this is a theoretical value, while this is experimental value. This is experimental value. Okay. Here, molecularity is less than or equal to, sorry, maximum molecularity. Maximum molecularity is less than or equal to 3. Here, order could be greater than 3 as well. It can take a values as high as possible. Okay. And molecularity depends on pressure and sorry, independent of independent on pressure and temperature, while this is dependent on pressure and temperature. Got it? So these are a few important differences between molecularity and order. Got it? Now, identifying order is one of the challenging things which we need to do. So, first method we will see is experimental method. Experimental method for determining. So, suppose if you have been given A plus B is giving 2C. This is experiment 1 here. Then at time t equal to 0, if you notice the concentration, let's say this concentration is A and this concentration is B and this is not there. At after some time, now this will become A minus X, B minus X, and this will become 2X. Correct? A minus X and B minus X here. Okay. So here what we do, we will figure out what is the rate in terms of this rate of the reaction here. So rate of reaction will be equal to K of the reaction into A raised to power of you know some, I could write this in terms of some P and B raised to power of some Q, some order here. Okay. So taking this into account, so we will be able to figure out what is its rate at a particular time. Okay. Same thing we do with experiment 2 here. Same thing we do it for experiment 3 here. But this time we will vary the concentrations. Correct. So here experiment 2 we will vary this concentration. Experiment 2, possibly I'll vary the concentration maybe 2A times. Then what will happen? Similarly, if I do experiment 3, in this case we'll have 3B times. Then what will happen? So then compare the rates for the same amount of time. For same amount of time, what will be the rate here? What will be the rate here? And what will be the rate? Or we generally write it as initial rate also. So initial rate will be equal to K reaction into initial concentration power P, initial concentration power Q. And if I write the same rate for, initial rates for all of these three, then we will compare how does that vary? How does that A varies? How does B varies? And how does C varies? Based on that, we will calculate what is the order. I'm expecting that you guys are aware of this type of methods. Given any data, there will be 3, 4 experimental points given. Concentration of A naught, B naught, C naught will be given. Initial rate you need to write down. Based on initial rate, calculate the constant value, rate constant value, and from there you will figure out, what will be the order of the overall reaction. Okay. So I'm guessing that that is something which you know that, right? Next, let us see if you have to calculate the order of the reaction. Clear? What is the other method? Second method. Uh, this is from mechanism of the reaction. The mechanism of the reaction is given. Then how do we calculate? Within that, we have two methods. One is equilibrium method. The other one is steady state approximation method, SSA. Okay. Suppose, let us take one example. If overall reaction is given, 2O3 is giving 3O2 gas. This is the overall reaction given. Okay. At the same time, how the mechanism is happening, that has been mentioned to us, in which step 1 is given as O3 gas, which is in equilibrium with rate constant K1 and K2, and O2 gas plus O gas. This is how it is being given. And then step 2 is given as O3 gas plus O gas, K3 to O2 gas has been given. Okay. And it has been said that this is a slow step, this is a fast step. So if you notice first equilibrium method, based on equilibrium method, what we will be doing is we'll write first the rate of the reaction. Rate of reaction can be written as K of the reaction. In this case, K of the reaction is K3, K3 into O3 into O. And remember, a rate should always be expressed either in terms of reactants or products and not intermediates. And if you notice O here, O is an intermediate. Okay. So I need to eliminate that term. So for which what I'll do, I'll write K equilibrium, which is K1 by K2. That is equal to O2 concentration into O divided by O3 concentration. So from here, O concentration will be equal to K1 by K2 into O3 by O2. This is the nascent oxygen concentration. So therefore, rate will be equal to K3 into O3 into K1 by K2 to O3 by O2. So what we are getting is K3 K1 by K2 into, we'll get this as O3 square by O2, or which can be written as some constant K, big constant K into O3 power 2 and OT power minus 1. And you can see these two are, reactants and products. So we can write the rate in terms of reactants and products. And what we are noticing is that the order of reaction in this case will be 2 minus 1, which is 1. Okay. Now, if you write the steady state approximation method, what do we get? See, according to steady state approximation, what we assume is that during the reaction progression, the rate of change of intermediate is always zero. Any rate of change of intermediate is zero. How do we see that? What is the change that is occurring to rate of the intermediate? See, intermediate is forming from the reactant side and it is losing towards product side in the second equation. So if I write that in terms of reactant side, I would be able to write this as K1. I mean, using the rate law, I can write K1 multiplied by O3 minus K2 into loss is in the opposite direction. So O2 into nascent oxygen. This is how much it is gaining or losing from K1 and K2 equation. And from K3 it is only losing. So we'll write it as minus K3 into O3 into O. And this has to be kept 0. So you can notice that O will be equal to K1 O3 concentration divided by K2 O2 concentration plus K3 into O3 concentration. And if I write the rate now, rate of the reaction is equal to K3 into O3 into O. This is what intermediate we were able to figure out, and we need to replace that. So K3 into O3 into K1 into O3 whole square divided by divided by K2 into O2 plus K3 into O3. So this is what we have. And approximately, if you notice that K2 and K3, if you compare, right, K3 is a very, very small value because in slow steps, what we can say that here, you can always comment on this fact that K1 might be far greater than K2, K3, and K2 might be far greater than K3 because of which the rate has such difference. So from there, we could notice that if K2O2 and K3O3 are concerned, this can be ignored. This can be ignored. So we can say on ignoring that, we will have rate now will be equal to K1 K3 by K2 into O3 whole square divided by, O2 divided by O2, which is same as what we got earlier. So K1 K3 by K2. This is the same kind of rate which we got earlier here. So you can see that into O3 raised to power of 2 and O2 raised to power of minus 1. Right. So remember, when you are doing steady state method, you just have to use this case. Okay. Now let us see how the PYQ has been asked in here, how the previous year question has been asked. One nice question has been asked here, multiple correct question. They have given these two steps, beta. Step one is given as A given B plus C with K1, and step 2 was given A plus C is becoming B plus D, and this was K2. Okay. And overall reaction is 2A is giving 2B plus D. Okay. So he's asked which are correct statements. Which are correct statements? The first statement, I mean option A, was given as B is reaction intermediate. B is reaction intermediate. Second, C is reaction intermediate. Okay, C option given is this is B option. C option was given as, using SSA, order of reaction, is 1. Option D is given, rate constant of reaction is equal to K1 by K2. Now check these off 4 options. Which one seems more appropriate here, everybody? See, this is the overall reaction. So in which you don't see C present in it, correct? Which means C is the actual reaction intermediate. So therefore, this option B is correct. A is not. Next. Using SSA, what I could say, dC by dt has to be 0, which implies where is C produced? C produced is in 1 and it is losing in 2. So K1 into A minus K2 into A into C, that is equal to 0. So from here, C is equal to K1 by K2. So it is just remaining constant as K1 by K2. So rate is always written for the slow step. As I didn't write that, it is given as here it was already given K1 is far greater than K2, which shows that K2 is second step is the slowest step. So rate is equal to K2 into A concentration into C concentration. So therefore, A concentration in this case, K2 into A concentration into C concentration in this case is equal to K1 by K2. K1 by K2. So we will get this as only K1 into A. So order of the reaction is 1. So order of the reaction is 1 and that is equal to K1. So it is independent of K2 value as well. Okay, so which one is correct now? Rate constant of the reaction is equal to K1 by K2. That is incorrect, right? Overall rate is only K1. Using SSA, the order of the reaction is 1, which is correct. So, which means these two options are correct, B and C. So, I suppose all of you got this point,
Yes, sir.
right? Another question which was asked on a similar line, see this JE question, which are correct from the mechanism, which uh, which are correct, which are correct statements from mechanism. Step 1, step 1 given was A plus B is giving C plus D. Step 2 is given as 2C is giving F. Step 3 is given as F plus B is giving 2A plus G. And overall reaction. Okay, so sorry, option A, overall reaction, overall reaction is 3B giving 2D plus G. This was one option given. Option B, A, B are reactants. Option C given is A is catalyst. A is catalyst. D is C and F are reaction intermediates. C and F are reaction intermediates. Okay, right. So now notice this one. Now, if you notice the overall reaction, what is that we are adding? You add step 1, step 2, and step 3. You will see that B is present here, and B is present here. And overall, I need to get 2D. So that means I need to multiply 2 here, right? And then add all of them. So CC will get cancelled, AA is getting cancelled, and G is remaining, D is remaining. Which are getting cancelled is F and C is getting cancelled here, correct? And C and F are only on the product side, isn't it? Not from the initial step. Not from the initial step. They were only starting to form on the product side first. And from there, they were forming on the product side. And then that is getting eliminated in the overall reaction, which makes A and B as reactant. First overall reaction, 3B giving 2D and C, that is correct. A and B are reactant is not correct. Reason being, A is getting consumed overall, which means A, which was initiated but not a part of the reaction. That is what we call it as catalyst. And C and F are reaction intermediates, which is making sense because with the use of reactant, you're gaining an intermediate out of that. So C and F are intermediates, while A is a catalyst here. Okay. So I hope all of you understood how the questions are framed here. Okay. Clear? Now, a general statement which you need to be always clear, okay? General statements, if they are asked in exam, about orders. Just be clear about it. First statement is, every reaction has an order. Every reaction has an order. Second statement, partial orders are never negative. Next, partial orders are always integers. Next, single step reactions. Single step reactions. Clear? Order is equal to molecularity. Next, zero order. Zero order is always complex. Zero order is always complex reaction. Next, uh, rate constants. Rate constants are always positive. Next, you know, rate constants have same dimensions. Rate constants have same dimensions. Okay. So if you compare these statements, right? First statement, rate every reaction has an order. Not necessary. It is only for those reactions which are moderate. If they are extremely fast, then we cannot define any order for that. Okay. Next, partial orders are never negative. Okay, incorrect. They could be negative as well. Partial orders are always integers. Not correct. Again, they could be uh, fractional as well. Single step reactions are order equal to molecularity is always correct. Zero order is always a complex reaction. That is correct. Rate constants are always positive. That is also correct. And rate constant have same dimensions is incorrect. Rate constants will have various dimensions as well. In fact, based on the dimensions, we should be able to figure out what is the order of the reaction. Got it? Based on the dimension, we should be able to figure out what is the order of the reaction as well. Clear, everyone? So I hope these points are clear. Okay, right. See, now let us focus more on zero order reaction for today. Okay, we'll just quickly go through it once. I'm sure how to derive it and all you are aware of. I'm not getting more details into the derivation part. Just directly check it out. Zero order reactions. Suppose A is giving products. A is giving products. Then rate R can be written as minus dA by dt, which will be equal to K rate constant into A raised to power of 0. Then we call it as a zero order kinetics. Okay. And on integrating this from C naught to Ct of dA, which is equal to K into integral 0 to T dt. So on doing that, we are getting it as Ct is equal to C naught minus Kt. And this is the equation you should remember for zero order kinetics. Okay. This is the zero order kinetics. Okay. Because in zero order kinetics, you would notice that, uh, the concentration term with respect to time is varying linearly. Okay. And it will come to an completion also. Correct. So this is that initial concentration C naught, which I have written, and time for completion, time for completion will be when Ct is equal to 0. So if Ct is equal to 0, T is equal to C naught by K. Okay, this is the time for completion. And then if you notice what is the half-life? Okay, T50 or T half-life is when Ct will become C naught by 2. So in that case, T half for zero order reaction is coming out to be C naught by 2K. Okay, this is about the zero order kinetics. Clear? Now, what are the other graphs which you need to learn? Other graphs which you need to observe for zero order will be first how the rate is varying, rate versus concentration. Got it? So, even if you change the concentration, rate will not change, it will remain constant because for zero order, it is independent of concentration of the reactant. And if you notice T half, how T half is changing, T half actually directly proportional to concentration. As the concentration increases, T half will increase. Alright. Last thing we need to know is what are the examples. Examples are, mainly decomposition on a metal surface. Any decomposition of metal surface is a zero order kinetics. 2 pH3 on nickel, it will become P solid plus 3H2 gas. Okay. So 2Hi gas in the presence of on the presence of gold, H2 plus I2 gas, and 2NH3 2NH3 in the presence of platinum, giving N2 gas plus 3H2 gas, or H2 gas plus Cl2 gas combining to form HCl on a metal surface or light metal surface or a light here. So that is also a zero order reaction. Okay. So mainly zero order reactions are observed when you are preparing some compound, like this in light, or you're using metal surface on which you are decomposing the gases. So then those are first order, zero order kinetics. Next.
Sir,
Yes.
excuse me, sir.
Hmm.
Sir, is the hydrogenation of unsaturated hydrocarbons is also zero order?
Zero order. Yes.
Oh, okay, sir.
Yeah. Next. See, generally how you need to observe here is suppose uh, as a simple arithmetic, you need to know this. If you have, let's say, 10 molecules and you are getting changed into 5 molecules over time, and then it is becoming 2.5 molecules, and then we have 1.25 molecules, and so on. Then the time taken from here to here, right, will be 5 minutes, isn't it? Because it is dependent on initial concentration, right? So from here to here, it will be 2.5 minutes, and here to here, it will be 1.25 minutes, and so on. Clear? This is the amount of time taken. So suppose if you asked for a zero order kinetics from 10 moles, if a reactant is moving to 1.25 moles, then how much amount of time is being taken? Correct? Considering the considering the T half is 5 minutes. So initially, if it is 5 minutes, then it will be 5 minutes plus 2.5 plus 1.25 and so on. This is how it will vary. Got it?
Yes, sir.
Similarly, if it is given T3 by 4, let's say if it is given T3 by 4, T3 by 4 means when the concentration is becoming 1 by 4. So 3 by 4 is the amount that has been lost. This is again a confusion with students. Please be aware of it. When we write 3 by 4, 3 by 4 is the amount that has lost, and the remaining amount is 1 by 4 of A naught. So now basically you're writing it for 1 by 4 of A naught. So 3 by 4 will be equal to 3 A naught by 4K of the reaction. Just like how we had, T half is equal to C naught by 2K. Now that will become 3 C naught by 4K. 3 C naught by 4K. So suppose if it is 1 by nth life, 1 by nth life, then how do we write? Then we'll simply write as 1 by n is equal to A naught by n k of the reaction. Okay. So it is time taken for completion of 1/n of the product. Okay. So I suppose these reactions are clear, and all the enzyme catalysis reactions are also zero order kinetics. Okay. In surface chemistry, if you recall, those reactions where we have an enzyme is present, right? So enzyme catalysis which we do, those are all also zero order kinetics. So I'll just put that also here. Enzyme catalysis. Catalysis reactions. So these are best examples for zero order kinetics. Okay. Done everybody? Right. Okay, guys. So we'll stop it at zero order for today. Okay. One second.